So this question is about finding stress due to bending and then actually shear stress. So note that the two are different, and in the case of bending stress here, then we're talking about the Missy equation, m over I is equal to sigma over y. So sigma is the bending stress, or stress due to bending, and then when it is shear stress, then we're talking about the Fabry equation. So tau is equal to F A y bar over B I. Okay, so the two are different equations and different things, so don't confuse the two. So the first one is to find the bending stress. Well, actually it's to use the maximum bending stress to find the largest allowable load, but we are simply going to use the Missy equation. Right, so we need to find for the Missy equation, to use it we need to find the I value. The I value is of this section here. It's a symmetric section, and therefore immediately we know that the neutral axis must be in the middle. So remember that symmetric sections, neutral axis is in the middle, so we don't have to find y bar. I is actually quite straightforward here. It's an application of BD cube over 12 of the external rectangle minus the I of the internal rectangle. So external rectangle 100 times depth BD cube over 12. That's the outer box, okay, like that. Outside minus the inside. Inside is this one, so minus the inside, so it's minus. So breadth, that's 100 minus 2 lots of 12, because there's a 12 thickness there and the 12 thickness there. So it's 100 minus 24, that's the B. The depth is 150 minus, again, 2 lots of 12, so it's 150 minus 24 BD cube over 12, and that gives us an I value of 15.4 6 times 10 to the 6 millimeter to the power 4. Okay, so that's the I. So this is the beam. You should be able to work out the reactions, and then the bending moment diagram you should be able to sketch out just like that. There's a load of 3 on that side, so the bending moment is bigger there. Now you don't have to set up the bending moment equation and differentiate to find the largest values for the bending moment and all that, because the bending moment made out of 3 straight lines. So you know where the maximum will be. It will either be at B or at C. And since the load is bigger here, the bending moment is bigger there, because the reaction is bigger there. Okay, so you should be able to work out that the largest, well, let's give you the reactions. You should be able to find, taking moments, that the reaction here is 27.14 W, and then on this side is 22.8 W, but the bending moment maximum here is 5.428 W. Okay, so use the Missy equation, m over I, so is equal to sigma over y. So the bending moment 5.428 W. Check the units. So I, this comes to 15.46 times 10 to the 6. For millimeter to the 4. Actually change using millimeter, that will become 5428.6 W. That is equal to, using the stress limit, sigma 340 newtons per millimeter square, so it's 340, and then y is, to find the largest stress, you go from the largest vertical distance from the neutral axis, so that's the y, so that would be 75, and that then gives us a W of 12.9 times 10 to the 3 newtons, or 12.9 kilonewton. Okay, so that's part A. For part B, we need the shear force to give us the shear stress. So let's remove that bit. The shear force diagram, here it goes up, goes along, comes back down, and goes along down to here and across like that. So the two big shear force values are either this one or this one. So you've got to work out which is the bigger value, and if you do it properly, you'll find that this is 67.86, and this is minus 57.14, with W of 25. So that will be a 75 kilonewton, and that will be a 50 kilonewton. Okay, so the largest shear force value is this one. So we're using the Fabry equation. So stress tau is equal to Fay bar over Bi. So F is this 67.86, and we want the largest shear stress, so we need to make a cut at the neutral axis level, because, so let's do this. Let me draw this. So I'm going to draw this like this. And then the neutral axis is in the middle. Okay, so the shear stress distribution is always maximum at the neutral axis, 0 top and bottom. So if we want the largest shear stress, so tau max, then we make a cut at the neutral axis level, and B is the length of that cut. So B is, so if I made the cut, let me just now remove the bottom. Okay, so B is the distance we've cut, so it's that plus that. So B would be 24. Okay. Because there's this bit and there's this bit. So F, well, so far we got F is this 67.86 times 10 to the 3 working in newtons. So F AY bar over I, Phi B, I, well, I is this value that we've calculated before, so I is the 15.46 times 10 to the 6 of the whole beam. Okay, there's that. Then, so in the equation so far, that leaves us with the AY bar, Phi B, so we still have this AY bar. AY bar is the area, so A is the area, Y bar is the distance of the centroid to the area. So the area is this bit. Okay. So there's that. Probably the easiest way to calculate those two, that area, is to take that area and minus the air gap, minus that. So let's do the AY bar then of the, so let's do the AY bar of this bit. So you've got that area, which is 100 across times 75 down, and the Y bar, so distance from the neutral axis to the centroid of that light blue, so that's a half of that, 75 over 2. Okay. Need to just make some space here. Hang on. Okay. Now need to take away the orange bit. Okay. So it needs to take away the AY bar of that. So that is the distance across and the depth down, and then A to the Y bar is there, so that's 63 over 2. Okay. So all of that is Phi B, that's the shear stress, shear force, that's the AY bar, B times I, and that equals 20, something like 24 newtons per millimeter square. Okay, that's the shear stress.